Okay, stats. This is a continuation or part B of section 9.1. We're going to go through example 1, and then I'm going to go through also a problem on your homework assignment just to get you started on that, because it is a little bit different. And then I'm going to post one more video for section 9.1, which is the confidence interval. So this will be the next video or tomorrow's section that we'll do. So in example 1 here, I think you guys kind of found out from yesterday's stuff that some of these formulas are pretty lengthy. So they're going to have us actually pick apart and figure out what some of these things are for this first example. So let's see, proportions of cars with rear license plates only. Okay, so we're talking about Connecticut versus New York, and we're talking about like the percentage of cars that only have rear license plates. In the state of Nebraska, most people have both front and back license plates, but I guess it's not a thing always in New York and Connecticut. So they are saying that in Connecticut, of the sample of 2,049 drivers that they did, 239 of them had only rear license plates, which is a pretty big chunk. That's 11% or almost 12%. That only had rear license plates. Okay, so that's our p hat. P hat always goes with our sample. And p hat 2 would be the other sample, which would be New York. And out of New York, they surveyed 550 people, and of those, only 9 of them had rear license plates, which is less than 2% here. Okay, so basically we're going to be comparing these two, and we're testing the claim that these two percentages are the same as each other. Okay, now it's not likely that they're going to be exactly the same, but they're saying is about 12% close enough to 2% to say that those have the same number of rear license plates or same percentage of rear license plates for these two states. I'm guessing not. I'm thinking 12% is way, way, way different than 2%. So I'm going to say that we're probably going to reject this, but we'll see what this looks like. Okay, so the symbols that we're going to use for our claim and for our null and alternative hypothesis is just P1 and P2. So we're going to claim that the percentage for the first state, or Connecticut, is going to be the same or equal to the percentage for New York. Okay, so Connecticut and New York are going to be equal in our claim. Okay, so that goes with our null hypothesis is always going to be equal to, just like before. So P1 equals P2, and then we're going to say P1 is not equal to P2. So if we end up rejecting the top one, then P1 would obviously not be equal to P2, and our claim goes with the null hypothesis. Okay, so just kind of similar to how we did this before, except our test statistic is really kind of disgusting to conclude. So we need to find what Z is, and I'm going to write the formula out for Z. It's up at the top if you don't want to rewrite it. P hat 1 minus P hat 2 minus P1 minus P2 over the square root of all this junk. P bar, Q bar, N1 plus P bar, Q bar, N2. Okay, that's what he is. Okay, so I'm going to write up here also some information that we have. Like just looking at the formula, I need to know what P1 hat is. I need to know what P2 hat is. P1 minus P2. Okay, I kind of talked about that in the last video. If we're assuming that P1 and P2 are equal to each other, okay, this is kind of another way of saying, like, if I would take P1 and subtract P2, or like if I move that P2 to the other side, P1 minus P2 would be equal to 0, because there'd be 0 left on the right side. Okay, so this guy is always going to usually, I think always, be 0. And then we need to figure out what P bar is, Q bar is, N1 is, and N2 is. Whew. That's a lot of information that we need. Okay, so we already know that P hat 1 is 0.117, Q hat, or P hat 2 is 0.016. Those two things that we know. Okay, I can also figure out what N1 and N2 are, and those are going to be the 2049 and the 550. Okay, those are the total number of people that we sampled. And then P bar and Q bar, if we look at our equation up here. P bar is adding the x's together and dividing by what we get when we add the n's together. Okay, so if you want to write it out, you sure can. I write out everything. So I'll put a little arrow here. Okay, P bar is adding the x's together. Okay, the x's are going to be the 239 and the 9. So I have 239 plus 9 as my x's divided by 2049 plus 550. Okay, so something like that. That's what I'm going to get for my P bar. Let me write this out. 239 plus 9 and 2049 plus 550. And that gives me 0.0954, let's say. Alright, so P bar is 0.0954. To find Q bar then is 1 minus that answer. Okay, and that's going to give me 0.9046. 0.9046. Oh, what an ugly, ugly, ugly deal here. Gross. Okay. Alright, so test statistic. Really disgusting. Alright, let's start plugging junk in. So I'm going to do P1 minus P2 on the top. Really, I don't have to do the minus 0. But P1 minus P2. 0.117 minus 0.016. That's going to give me my top number. So I have 0.101 on the top. On the bottom. Holy cow. Okay, I'm going to do Q bar, or P bar Q bar over N. Okay, so P bar is 0.0954 times 0.9046 divided by the 2049. Okay, oh my gosh, this number right here is 0.000042. If you don't want to write that out, you don't necessarily have to. I'm going to just take and add that to parentheses 0.0954 times 0.9046 divided by 550 this time. Okay, so that's P bar Q bar divided by N squared. Or not N squared, N2, which is the 550. Okay? Alright, so if I add those two numbers together, I get this guy, and then I want to take the square root of that. Square root of the answer. Okay. Alright, so my bottom number, after I take the square root, after I've already taken the square root, is 0.0141. Okay, and then I take my top number divided by my bottom number. 0.101 divided by 0.0141. Oh my gosh, finally. Okay, 7.16. Whoa, that was a lot of work. Okay, but we're pretty well done now. Okay, pretty well done. 7.16. Gee, many Christmas. Okay. All right, now everything is the same. Now that we found our test statistic, that's the ugliest part. Now everything is the same. We're trying to test the claim using a 0.05 significance level. Okay, since it's equal, we have two tails. So a tail here, a tail here. If it's 5%, then that means there's 2.5% in each. Okay, which means 95% is here. Okay. All right. So the p-value method, I would have 0 here, 2.5% would go here, 97.5% would go here, and 100% would go here. Okay, and I'm kind of just looking at where this thing's going to fall. Okay, so 7.16 is the number that I'm going to look up, and I'm going to look that up on the Z table. Okay, positive Z table. Okay. 7.16. Okay, my numbers only go to 3.5, but it says anything above 3.5 is 99.99. So this guy is going to convert to 99.99%. Oh, I can go down here. 99.99%. And that is going to fit right here. Okay, that guy right there. Okay. All right, now what we need to do from that point is figure out what our conclusion is. So using the p-value method, since he's in the dark, we're going to reject. So we reject the null hypothesis, which means the claim is, since the claim went with the null hypothesis, the claim is invalid. And we can say that license, I don't know if I spelled that right, license plates differ from Connecticut to New York. Because we were assuming that they were the same, but they are not. License plates differ, okay? If you're doing that the critical value method, what you would do is instead of doing this 0, 2.5, 9.5, 100%, on my positive z-score table, I'm going to look up 95%, this middle number. Okay, 95% is going to be 1.96 instead. 1.96 and negative 1.96 and positive 1.96. Okay, and then I just look at the 7.16 and compare to the negative and positive 1.96, which is still over here in the dark. So I still have the same conclusion, okay, as I should. I should always have the same conclusion, but it's just how you want to compare, okay, whether you want to convert these to decimal or to percentages first, or whether you want to convert them to z-scores first, okay? So that's kind of that procedure, all right? I'm going to do one more for you, and that is going to be looking at number 2, okay? So number 2, in a large clinical trial of this many children, so 396,000 children, they were randomly assigned into 2 groups. The treatment group had this many in it, and the placebo group, let's see, the placebo group had this many in it, okay? Okay, so the 396, that number really doesn't do a whole lot for me because they're just saying that's the total number that I've separated out into the 2 groups, okay? So your total number is n, but since we have 2 n's, we have an n1 and we have an n2, so that's what our 2 numbers are going to be, okay? The first number is going to be 196, 889, and 199, 919. That's what he is, okay? All right. So, let's see. Okay. 29 of the first group developed the disease. That's going to be my X1 is 29. X2 is the number that developed the disease in the placebo group, which is 102. Okay, so then I can use that information to find P bar 1 and P bar 2. And what those are just going to be is the percentages. So if 29 out of the 196,000 and 102 out of the 199,000. Okay, so I can do those as percentages. I know this seems like really cumbersome, crazy formulas, but once you do it a couple times, it's really not terrible. And I'm not going to give you too many problems to work on here. So 29 out of 196, 889, it's going to be really, really long decimal. 0.000147. Okay, the second one is 102 divided by 199, 919. 0.000510. Okay, we'll go 6 decimal places for each one of those. Okay. And then, let's see, I'm looking at the other information that we had on the notes. Let's see, what other information do we need from the notes? We have P1 bar, we have P2 bar, or P1 hat, P2 hat. We need a P bar and a Q bar. P bar and Q bar. We need what those guys are. And then N1, N2, we have those. Okay, so P bar is going to be the X's added together over the N's added together. So X is added together is 29 and 102. I should do parentheses around those. Parentheses 29, 102 divided by 196, 889 plus 199, 919. And that's going to give us 0.000330. Part of this, the ugly part of this is because the numbers come out to be so gross, or really long decimals. Q, I just take 1 minus that. So it's going to be like 0.99999 something. 0.999670. 0.999670. Holy cow, that's a lot of numbers. Okay. Wow, and I haven't even read the whole thing yet through. Okay. Consider the vaccine treatment group to be the first sample. So that's the one. The treatment group was the first sample, N1. Okay. The placebo group is the second sample. Assuming a 10% significance level will be used to test the claim. Now my claim is that P1 is less than P2. And P1 equals P2. And P1 is not equal to P2, or P1 is less than P2 is what we're going to assume for our alternative hypothesis. Okay. So the only thing different here is that I'm only going to have one tail, and it's going to be the left tail. Okay. And a 10% significance level means all 10% is here, and I have an imaginary 10% here, which means I have an 80% confidence interval. Otherwise, everything else stays the same. Okay, so that was really the one difference that I wanted you to look at. So less than means one tail. We're going to do our test statistics of Z, and here is the ugly part. Okay, so here's our test statistic. This is what he looks like. Now we get some practice typing these things in. Okay, so P hat 1 minus P hat 2. All right, that's these decimal numbers right here. 0.00147. 0.000147 minus 0.000510. That top number is going to be a negative 0.000363. Okay, now I'm getting a little bit better at this. Let's see if we can type this in. So P bar, Q bar over N1. All right, so I'm going to do this. P bar 0.000330 times 0.999670 divided by N1. That's my N1. N1. Nope, N1. Holy crap. 196,889. Enter. Okay, wow. Plus P bar 1, or P bar Q bar over N2, 0.000330 times 0.99967 divided by N2, 199,919. These are awful, awful, awful numbers. Okay, there's that. So that is this whole thing right down here, P bar Q bar divided by N1 plus P bar Q bar divided by N2. But I need to take the square root of that now. So last thing, square root of that answer. And haha, finally, we have a number that's still really disgusting, but that's okay. 0.000577. We'll go. Okay? And then we just need to divide those. So I'm going to take negative 0.000363 divided by my answer. And I get, finally, negative 6.29. Ha! Perfect. Okay. Negative 6.29. So if I do the p-value method, which is the one that I know that you guys like, I would do 0%, 10%, really this would be 90% and 100%. That's what he would look like. And then I need to figure out where negative 6.29 lives. So I'm on my Z chart, and I am on the very bottom, no, very top actually. Anything that's less than negative 3.5 is going to be 0.0001. Okay, so 0.0001 or 0.01%, which is going to be all the way down over here. Okay, so that is going to be a reject again. So we're rejecting this guy, except in this case the claim is going to be valid because the claim went with the alternative hypothesis. Okay, so our claim in this case is valid, and we were claiming that the treatment group had a lower percentage than the placebo group. Okay, so the treatment actually is helping. So that's what the claim is kind of saying. If the claim is valid, Treatment is less than placebo, so treatment is helping. Treatment is helping, okay? I know this seems really super cumbersome and awful, especially since the numbers are really gross, but just hang in there. It will get better, I promise, and the more that you do these, the easier it will become. I'm only going to have you do number one, and number one is just listing out what each variable is, okay, which is kind of one of the hard parts. And do number three, just part A, though. They say test and do the confidence interval method. We're not going to do the confidence interval method until after I post the next video. So just do number one and do number 3A. You know, try to work through it. It should be a little bit better numbers for number three, just because they're not in the thousands. Well, this one's in the thousands, but not huge, okay, like we had before. So the numbers for number three should be a little bit better, okay? There you go.